All right, dude, we are live. What's up, guys? This is Dem Keys, and today we are going to continue learning about ESP32 Rust things, but today we're going to be specifically focusing on PWM or pulse width modulation. And sorry. And after yesterday's stream, I did some more research on how PWM works exactly, and I discovered something interesting. See, I had two doubts. So my first doubt had to do more with um, going back to like the analog level. I always, holy shit, I always had this doubt um, about how exactly, like let's say we're talking about a simple battery LED resistor circuit. Um, I always wondered if the LED lighting up was the result of current flowing through the circuit over time, or if it was an instant thing. And one other issue that I used to have in the past when trying to understand analog electronics, that's actually one of the reasons why I never managed to get too deep into analog electronics. It's because I would be trying to learn analog electronics, but then I would like in order to understand it, I would end up going really deep down into not just regular physics. Somehow the research would end up going down to quantum physics. Um, and regular physics by itself would be very complicated for me to understand. At least, this kind of stuff that I was looking into. On the regular physics level itself, it would have been complicated enough for me to understand. Going down to the quantum level, that actually, I don't even know if I would call that a lower level or a higher level. That's how little I know about quantum physics. But yeah, I would have this issue where it would start going down to that level. And it was one of those things where it's like, okay, I'm trying to understand how even something as simple as as a battery LED resistor circuit is working. More specifically, I'm trying to understand how how is it that the current flow is making this circuit work? How is the current flow from negative to positive, or as they teach you in conventional, at the beginning, as they teach you at the beginning of learning electronics, positive to negative, how is the current flow from one side to the other making the circuit work exactly? And of course, the answer to that would depend on the various components that are within the circuit, because these various components on a physical level, or I guess molecular level, atomic level, let's say physical level, on a physical level, each of these components work in different ways. A resistor, a capacitor, a transistor, and a diode do not work in the same way. And the fact that they don't work in the same way, the fact that each of these each of these components work very differently on a physical level is what makes them unique, and is what makes it so we have these different components that we need to put together to form a circuit to create different types of behavior, right? Where was I going with this? I kind of forgot where. So okay, yeah, I've always had this issue where I would keep trying to go down to the lower level, and that's one of the reasons why I never managed to move forward with analog electronics or go deeper into analog electronics. It's because I would usually get stuck at the basics. More specifically, within the basics, I would get stuck on how certain concepts were working, and in order to properly understand those concepts, I would have to go down to the physics level, and things would start to get more complicated there. Okay, so we're going to keep that aside for a second. Okay. what I was wondering, in terms of PWM, or the doubt that PWM brought back, was me wondering whether an LED lighting up is a result of current over time, or if it's an instant current thing. Like the moment the current touches this component, it lights up. And to simplify the answer, like grossly oversimplify the answer, um, it's not over time. It's an instant thing. In the past, where you had LEDs that where like um, a wire would heat up, or an element would heat up, and then that would slowly create a glow. In those days, yeah, you would have like a something that would gradually, even though that was also fast, but gradually it would light up, and then once you stop giving it current, it would gradually dim down. But even that gradual was pretty fast. This was previously. Apparently now that's not a thing. Actually, for I think a good few decades that hasn't been a thing. Um, and I don't think those were called LEDs either. Yeah, I just I was thinking about that as well. I don't think those were called LEDs. But yeah, yeah, okay. So uh Gemini answered my question regarding this. That yeah, for at least for practical purposes, yeah, it's instant. It's not a function of time. It is not something that is happening over time. The lighting up is not happening because you've given it current over time. It is happening the moment the current touches the what do you call it? The LED. And then that raised the question for me that, okay, if it's not over time, why is it that we require a resistor? That's where it gets a little bit interesting, right? Um, Actually, no, that's where it gets a little bit complicated and very interesting. That's what I was trying to say. Gemini did clear that up as well. Let me see if I close that conversation or if I still have it open. Because like this, we came down to this level while talking about PWM, because I was trying to understand PWM, and I had a doubt about PWM. I was wondering which one of the two is it, like in terms of my assumption of how this thing is working. I had two theories. One was that the way that this is giving signals to the LED or to the circuit, the way that the pin is giving signals to the circuit, that creates an illusion of dimming or lighting up. There's a similar thing that happens in I forgot what it's called. I don't remember if it's called a multiplexed circuit or Charlieplex. No, I think Charlieplexing is a um, it's a concept based on multiplexing. Hold on, let me just look this up. Um, okay, LED multiplexing. It says Charlieplexing. Charlieplexing is a technique for accessing a large number of LEDs, switches, microcapacitors, and other I/O entities using relatively few tri-state logic. So and so. Okay, it might have been Charlieplexing, not multiplexing. Though Charlieplexing is also known as tri-state multiplexing, reduced pin count LED multiplexing, complementary LED drive, and cross-plexing. So, okay, looking at the diagram, it was Charlieplexing. So, Charlieplexing apparently also follows a similar concept where it's creating the illusion of something being on or off by constantly turning a bunch of these things on and off, which that was kind of interesting to learn that what we are really seeing is due to our it's due to our it's due to the limitation of our perception, uh the limitation of how do I word this? It's due to the limitation of the human eye, because the human eye can only see up to a certain speed. Like in terms of state changes, the human eye can only see up to a certain speed, and past that point, everything becomes a blur, and your brain or your eye, whatever is responsible for this, basically just starts averaging everything out. And that averaging is what we are taking advantage of when we do something like PWM. Because apparently PWM, the way that it works, and this was like my first theory was this, and the second theory was that maybe it's just sending an actual analog signal. It's not. It's not sending an analog signal. I should try that though. Yeah, yeah, I should try that though, because we have DACs, right? Digital to analog converter. I should try that. I should see what the difference is between using PWM and DAC. That would be an interesting experiment to do. Um, what was I saying? Yeah, my first theory was this one, and my second theory was that yeah, it might be PWM might actually be an analog signal. It's not an analog signal. It is digital signals that are being um, it's digital signals that are being put out so fast and causing state changes so fast that they create the illusion of either on or off. And my understanding is this, that okay, if we have like, let me come back here, we have this nice interactive thing that we can use. So if we, let's say we set a duty cycle, this is one duty cycle, okay? One duty cycle um at one hertz, so that's one cycle per second. Okay, that's great. My theory is this: if it's happening at this speed, we are probably going to be seeing the on-off effect, because here this is one entire cycle. If we increase the frequency to um, 4 or even 5, if we increase the frequency, you can see now this goes on and off, on and off, on and off, um, 5 times a second. We should be able to see that. It's going to start to become faster, but we should be able to see that, right? And then this duty cycle thing is how long it remains on throughout that one cycle. So the combination of duty cycle and frequency creates this illusion of the LED being dim or bright. And that's kind of interesting. So with PWM, we are essentially taking advantage of the limitation of the human eye. Um, we're going to test this out once we've read up more on PWM, and we eventually get to actually doing PWM stuff practically. We're gonna test this out. Okay, okay. I don't want to end up yapping for way too long, and then we only get like, I don't know, an hour and a half to do practical, or to do the ESP32 electronic stuff. Let's jump into, actually, real quick. I also want to mention that I have been making some progress with Westterm, and I was trying to kind of, for lack of a better term, I was trying to fit Westterm into a box to try and understand um like what the deal is with this terminal. Because like, okay, with with the Kitty terminal, I did not have to do nearly as much manual configuration as I've had to do with Westterm. right? So this had me wondering that, okay, what's the deal here? What exactly is going on? And I think Gemini put it best. Gemini said that WesTerm is essentially a minimalist terminal. Um, and like I was making the comparison to something like NeoVim, because if you look at, like, I have NeoVim open right now over here. This is not just bare bones NeoVim. Bare bones NeoVim looks nothing like this. Let me see if I can show you what bare bones NeoVim looks like. Hold on. I don't. So I have NeoVim installed. I don't remember if I have Vim. I have Vim. Okay. This is Vim. This is also what NeoVim looks like, more or less, when you open it up. You're gonna have this thing, and I forgot how you enter. Okay, yeah, you hit I and enter insert mode, and then we can say this is a sentence. And when I'm done, I can hit escape and go back to normal mode. I kind of forgot because like I haven't I haven't looked at this kind of a layout for a long time, or this, well, lack of, a layout. I'm used to seeing like normal mode being mentioned in the bottom left, which you guys can't really see right now because the the screen is a little small. But there's a tab line. Oh, I could try something here. Yeah, here it is. So now you guys can see it. This is the tab line. I actually forgot that in NeoVim, the tab line at the bottom, it's kind of a part of another window, and so you can kind of like change the size of stuff. Similarly, when you do something like this, it's a similar situation going on. Yeah. Okay. What was I saying? Wait, let me open up my chat on my phone. So yeah, that's the tab line that I just showed you. I'm used to seeing that, but this is nothing what NeoVim looks like when it's bare bones. NeoVim looks like this when it's bare bones. Um, so if I wanna save the file, then I have to do, I don't remember if Control S works in this. Um, I don't think it does. Okay, so save. To save, we do colon W. Let's say test01.txt. The file has been written. To quit, we do this. That's how Vim and uh, from what I remember, even NeoVim looks pretty much like that, right? It looks nothing like this. You don't have like a which key menu. You don't have this, the Explorer menu. You don't have a tab line at the bottom. You don't have these. Uh, you don't have the buffer line, I believe it's called, uh, to show you buffers. I don't remember if you have like a. No, I think the window function, the split window functionality is there. Also, let me clarify. You do have buffers in NeoVim. Um, like it's a very heavily used concept. I'm talking about the aesthetics here. So like you don't have a line showing you the currently open buffers. You have to, like, there are other ways to find out that there are buffers and stuff. You definitely don't have a which key menu. You can't do something like opening up a key maps search window. You don't have any of this stuff until you configure NeoVim. And words. Holy shit! What just happened? Configuration. Configuration involves um, changing the settings within NeoVim itself. There's a whole bunch of Lua configuration that happens, and additionally, it involves installing a whole bunch of plugins using some sort of plugin manager, or even just manually installing plugins. In the case of manually installing the plugins, I guess the update process is not going to be handled for you. Also, the installation process is, I guess that depends on what type of plugin manager you're using. But with something like LazyVim, for example, um, well, with something like Lazy, the plugin manager, I believe, is called Lazy. With something like Lazy, you just have to specify the name of the plugin. So it's like a GitHub account name slash repo name, and then that has to be the link to that has to be the repo that's hosted on GitHub with a very specific file structure, and then Lazy handles all of the other stuff for you. It does the cloning, it reads the entire data from the thing, and it installs whatever needs to be installed. Additionally, you might need to do a tiny bit of configuration. That you probably need to do it manually, but they provide you with the code snippets for all of that stuff. Okay, back to Wes term. Uh, the point that I was trying to make, I completely forgot about that. Uh, the point that I was trying to make was that NeoVim, when you first install NeoVim, it's bare bones. It looks nothing like Lazy Vim, which is, um, let me open up NeoVim. This is Lazy Vim. And by default, NeoVim looks nothing like this. It looks uh, basically like this, at least from what I remember. Um, I could be wrong. I don't think I'm wrong though. Pretty sure it looks like this. Okay. Um, right. So, my I guess realization was that Web's term is it's kind of a similar thing. It's in a similar situation to NeoVim, where you get a very bare bones but packed with features terminal. Okay, similar to NeoVim, all of the stuff that these plugins in NeoVim are able to do, they're only able to do it because NeoVim has exposed that functionality. Out of the box, the functionality is not all being used. NeoVim, it's one of those things that it is packed with functionality, but you need plugins to use those functionalities. That functionality, to use that functionality. There's a lot, and I mean like an insane amount of features um, that are part of the NeoVim API. The NeoVim API exposes a lot of functionality, but the default tool set that you get out of the box, it doesn't always use all of that functionality. But this is what makes NeoVim so powerful. It exposes all of this functionality so people can develop their own plugins to then use that functionality, and then that's how you get to this situation where you have distributions. Distributions are essentially um, a mixture of very specific configurations and sets of plugins. So the configurations, when you say configuration, you would be saying something like, okay, changing various settings within NeoVim, setting various key maps, setting various like default settings, installing something like a plugin manager, and maybe a couple other things, right? And then further from that point, um, the distribution handles everything else. So with LazyVim, for example, there's a bunch of plugins that come installed by default. There's also there's a list called Lazy Extras, which is a bunch of community recommended plugins. You just have to enable the feature here and then maybe restart NeoVim, and it's gonna install the plugin for you. You're not limited to just these. Um, Hold on. I'm seeing a couple here that I feel like I haven't taken the time to look at all that much. I should visit this list again. Oh, you also have this very interesting concept that I found. So, like, if you look at this thing here, this says mini diff, and then you have mini files and mini move, and there's a bunch of other mini. Mini is actually a family of plugins. So you have many plugins for various different purposes, and it's kind of interesting how, like, you install this plugin, but then you enable certain um, you enable whichever smaller, very specific plugins you want from this plugin. I still have to do research around how this is supposed to work and how we are meant to be using this, because I haven't done it like the manual way, like installing Mini, and then within Mini installing very specific plugins from Mini. I haven't really done that. I'm slowly getting experienced with manually installing and configuring plugins. Well, manually still using LazyVim, but still manually. um I'm still slowly like building up my experience with it. It's kind of interesting. I've been using NeoVim for more than a year now, I would say. And initially, what even a couple of years ago, when I'd explored NeoVim for the first time, I I just I left it. I was like, dude, I can't do this. This is to be fair, at the time, I don't even know if the plugin ecosystem was like this level of mature. I don't know if the distribution ecosystem was nearly as good. This was like years ago, when I first explored NeoVim, and I was seeing a couple of videos from people saying that, oh yeah, you can get IntelliSense in terms of coding, and there's this you can do and that you can do. And I wasn't able to understand anything, and it kind of seemed like it would be more trouble than it's worth. And at the time, I was pretty happy with VS Code, so I didn't bother moving forward with it. And then last year, I can't even remember if it was last year or if it's been it's definitely been more than a couple of months. It hasn't been a couple of months. It's been a lot more. So I would say more than a year, or at the very least a year ago, when I first started exploring TUI based or terminal based applications. Um, it all started, by the way, with BTOP. Like, that's what blows my mind. It all started with BTOP. I'm not even exaggerating about that, because I was getting sick of using the system monitor on Ubuntu. It's a GUI application. I don't remember if it's called System Monitor or Process Monitor or whatever. It's basically the Ubuntu version of, or one of the Ubuntu versions of Task Manager on Windows. It's basically that, and was it's not like it was horribly slow, but it was slow. It was not fast at all. Um, Not to mention, I had actually discovered a bug, which fortunately I discovered it back then and not later on. But I had discovered a bug within that system monitor slash process monitor. I keep confusing the two. But anyways, within that system monitor, I had also discovered a bug. More specifically, within its UI, I had discovered a bug which would cause, I don't think it was a UI bug specifically, but like the system monitor is a GUI application. That's what I mean. I had discovered a bug in there where if you opened up any of the tabs that involved graphs in any way. So, like, there's, for example, a performance tab where they'll show you graphs for CPU usage, memory usage, network usage, and stuff like that, GPU usage. They essentially build a graph uh, over time. That graph or that tab, some sort of functionality within that tab would cause memory to fill up over time. And I'm talking like it would end up taking GBs of memory over time. I never figured out what the issue was, but I do know that it caused my system to kind of crash a couple of times. I don't remember if they were full on crashes, like full system reboots, or if Ubuntu managed to just crashed the application that needed to be crashed, and then it like logged out and allowed me to log back in. I don't remember which one. Some of them were definitely like full on crashes, and I had to like reboot, or the system rebooted, and then I had to like open up all my whatever I had to open. I had to open all that up again. um but yeah, so I'd gotten sick of this, and that's when I started looking up. Additionally, I was getting sick of looking at the system monitor on Ubuntu Studio, because that was another GUI application, which was equally as slow, if not worse. Like, imagine opening up the menu, and trying to open up the system monitor, and you have to wait for a good like 10 to 15 seconds before anything even shows up, and you have to wait for another 10 to 15 seconds for that entire UI to like stabilize so you can properly use it. And then when you click on a tab, you have to wait for a good like 5 seconds before the tab shows up. It was stupidly slow. It was crazy slow. So I was getting sick of it, and so I was like, okay, let me see if there's a terminal alternative. At the time, I didn't know too much about TUI applications. I knew that there are these applications that let you see on information in the terminal. I didn't know too much about TUI applications, so I didn't know that you had these frameworks that allow you to like draw they give you drawing capabilities within the terminal. So you can like draw panels, you can draw windows, you can draw buttons, you can draw borders around things, you can display images, you can write text in different places. I didn't know that any of this stuff existed. So when I started doing research, um, I started by asking Gemini that, hey, I want to see if there's like a terminal based alternative for system monitor. What are my options? Surprisingly, um, Gemini didn't recommend BTOP first. Gemini recommended something called Glance or Glances. I don't remember what it was. Hold on, let me look that up. I've not touched that thing since then. I didn't even try it out back then. Hold on. Um, uh, Glance app. Glance refers to several so and so. A self-hosted dashboard. Hold on. Was it called Glances, maybe? It was called Glances. Okay. Glances, an eye for your system. Yeah. Okay. So this was one of the TUI applications, I believe. I don't remember, or was this GUI? Hold on. Okay. Yeah, I can't remember if this was GUI or TUI. Okay, it says local terminal, web interface, and remote monitoring. Okay, all right. So this is one of the tools, and this thing was written in Python, is written in Python, and it seems like it's widely used as well now, which is great, awesome. That being said, Gemini had recommended Glances, and then HTOP, and then BTOP, and then top. I think that's how the list had gone. I don't remember exactly, but I believe that's how the list had gone. I asked Gemini for more information on all of these because I wanted adequate information before I installed something. And then I would have to uninstall it. And like, I mean, uninstalling from Ubuntu, it's not usually much of a mess, though it depends on how you went about installing something. Um, but yeah, I did research. I then also Googled for Reddit threads to get other people's opinions on which one they like the most. And it seemed to me like a lot of people were recommending BTOP. So I took a look at BTOP. There were people also recommending HTOP and just top. Um, top, I believe, is like the OG that these others were built on top of, or these others were inspired by. I don't remember if top was also inspired by something else, but yeah, I believe H top and B top were inspired by top. Um, Funnily enough, there's a Rust based system monitor called Bottom. I've tried that. I've tried that as well. It's a TUI application, but then I came back to BTOP because I kind of like whatever BTOP had going on. BTOP had like just the right amount of features that I needed. It got the job done. I just needed to make sure that I kind of um, reworked my workflow to be more um, to fit better within BTOP. So, anyways, I did research, and it turned out people liked BTOP a lot, and so I looked up BTOP, and I liked whatever I saw there. So I was like, you know what? Let's give it a try. I'll install BTOP, then I'll install HTOP, and if I don't like them, then I can always remove them because they are going to be installed using the apt repo. So it should be relatively simple to both install and uninstall. I'll hold off on glances. I won't install that just yet. And so I tried out BTOP and I liked it so much that I didn't even touch HTOP, and I completely forgot about glances as well. So, anyways, once I discovered that okay, now I can look at my system monitor in the terminal, that got me curious about what other things I could do in the terminal. And so I started by asking Gemini that, hey, what other things are possible? Um, and in fact, I would also like to learn. This was at the time. I was asking Gemini that, okay, what other things are possible, but also tell me how exactly is it that BTOP is able to do all of this stuff? Because I'm seeing like drawings, I'm seeing borders, I'm seeing lists and tables and graphs, and I'm seeing stuff that you would need to give a framework some instructions to draw. How is this happening? And then Gemini explained that yes, you have a library called ncurses, and I believe BTOP is built on top of that, or maybe there's a library that's built on top of ncurses and BTOP is built on top of that. It's one of these two. I believe BTOP is built on top of ncurses. Ncurses, it's essentially a terminal graphics kind of application. More specifically, I think UI. I don't. Hold on. Let me just confirm that ncurses. Okay, ncurses is a free software programming library that provides an API for developing TUI, okay, in a terminal independent manner. It optimizes screen updates to reduce latency, making it highly efficient for remote terminal sessions. So this was, I believe BTOP was ncurses based. Let me just confirm BTOP, because I could be wrong about this. Maybe it's using some other library. Not it's not words. Holy shit. It's not like it's a big deal, but like I just want to get the information right. Um Hold on. Okay, let me just ask Gemini. Hey, so I'm wondering how is BTOP able to do all this drawing in the terminal? Okay, since terminals are technically only meant to display grids of characters, BTOP and its predecessors like BPyTop and BashTop. I forgot about BPyTop. Yeah, yeah. Uses a combination of high density Unicode characters and ANSI escape codes to fake high resolution graphics. Wait, this doesn't use N curses? Hold on just a second. Wait, so BTOP's code is directly using uh, escape codes and Unicode chars. I thought it might be using um, some sort of library that does that. I don't remember why I thought it was N curses. Okay, let's see. You are absolutely right to suspect there's a middleman. While BTOP could print those strings directly, doing so manually for every different type of terminal, such as xterm, kitty, iterm2, etc., would be a coding nightmare. BTOP doesn't reinvent the... Okay, it doesn't. It uses a specialized TUI framework, FTXUI. BTOP is built using a C++ library called FTXUI, Functional Terminal User Interface. This library acts as the rendering engine instead of the developer manually so and so so and so so and so. Okay, why not use the standard, which is ncurses? If you've looked into terminal programming before, you've likely heard of ncurses. It's the industry standard used by HTOP. Okay, HTOP uses ncurses. I mixed up the info. Apparently, Vim also uses ncurses. It says Vim, not NeoVim though. I need to see what NeoVim is built on top of. But yeah. However, BTOP's creator opted for a more modern approach for a few reasons. Okay, you know what? That's good enough for me. Okay, now getting back to what I was talking about. Holy shit, this was a... Oh my god, dude. We are almost 45 minutes into the stream. What am I doing, dude? Well, anyways. So, um, yeah, that got me once I got into BTOP, then that got me exploring more and more terminal-based applications. And holy shit, ever since then, I've had a primarily terminal-based workflow. That is insane, dude. But yeah, yeah. My theory about WesTerm is that it is in a similar situation to, or it is a sort of yeah, it's a similar kind of situation as NeoVim, in that when you install NeoVim first, or when you install the application first, you get a very bare bones application. That's not to say that the application itself is limited. It's just that a lot of the functionality is not yet being used. The application itself provides you with a very powerful API, but the thing is, you need to extend this application by configuring it yourself. And the configuration could be either manual configuration or using plugins, which are pretty much also just, manually extending the capability. Um, yeah, yeah, I've discovered that because Western seems to have a lot of different types of features. Like if you hit Control Shift P on it, it'll open up the command palette, and there's a lot of functionality that you can access through that. There's also a search bar, so you can like search for various features. There's certain features that haven't been key mapped, so you have to key map them yourself, or use a plugin that does it for you. For example, the tab navigator. So in Tmux, I do Control BW, and then that shows me this entire thing. It's not just the tabs; it shows me the entire Tmux session. So we have lists of these Tmux sessions. I believe I can also collapse them. Yeah. So these are all the tmux sessions. And then the specific tmux session that I'm in, there's a list of all the tmux windows that are within that session. And then within each of those windows, I have an application that's running. Now, where was I here? Sorry, give me a second. I need to find, wait, wait. Oh yeah, I'm right here. Okay. Hold on. Why did I have trouble? Am I here? I'm here. Okay. Yeah. Okay. Okay. So similar to this, you have something called the tab navigator in WesTerm, which will show you a list of the tabs that you currently have within this, I think within this domain. Yeah, I was about to say within this workspace, but I'm not entirely sure about that. But yeah, I'm still exploring that aspect. I'm still exploring the multiplexing aspect of WesTerm. That's like the last thing that's remaining for me. That's the last piece of the puzzle. And once I have at the very least recreated the functionality that I'm able to achieve using a Kitty plus Tmux workflow, um, at the very least, once I've replicated that functionality within WesTerm, um, I'm I'll be ready to move on from the Kitty terminal. I'll be ready to start using WesTerm as my essentially daily driver. I still haven't like there's multiplexing related concepts that I haven't fully wrapped my head around, and I feel like I need to do a bunch of research because I maybe it's just me, but it seems like the documentation is a little bit lacking in that department. So I need to experiment a bunch to understand things. Like you have domains, you have local domains, SSH domains, and Unix domains. My understanding is that local domains are, or it's one local domain, which is where you open up various tabs, and they're part of that domain. But once you close the window, that domain closes. So those tabs will also pretty much die. Then you have an SSH domain which stays alive, and you can SSH into this machine to attach to that domain and basically load up all of those tabs natively on the other machine from which you have SSH'd into this machine. That's an interesting concept to me, because imagine like you can see the uh, multiple tmux windows that I've opened here. I have to SSH into my machine where the tmux session is hosted, and then I have to attach to that tmux session in order to get this, what I'm seeing here. But in WesTerm, when I do that quote unquote attaching, apparently it's going to open up all of those tabs natively within WesTerm. So they'll show up as native tabs, but they're still remote. So it's happening over SSH. That's SSH domains, from what I understand. So basically, that's one way to keep the session alive. And then you have Unix domains, which is similar to SSH domains, except it's more meant for local. So you can keep the session alive even after closing your terminal. You don't have to, that session is not going to die. But I don't think that that's SSH capable. I should see if there's a way to um, mix up the functionality between SSH domains and Unix domains. But yeah, that's I'm trying to explore these various multiplexing related concepts. Stuff like there's workspaces and sessions. There's Mux window. There's, like I mentioned, the various types of domains. There's a couple of more multiplexing related topics that I need to look into. And once I've wrapped my head around that, and I've reproduced this Kitty plus Tmux workflow there in the WesTerm way, then I'll be more comfortable with completely switching over to WesTerm, because it's a pretty decent terminal, to be honest. Okay, you know what? Now it's been 50 minutes. Oh, shit. Now it's, sorry, I hit my keyboard. Now it's been 50 minutes. This is crazy. I'm going to stop the Yap sesh and we're gonna start reading this. So yesterday we got done with this entire page. We read up on some of the math behind PWM. Now we are going to go to the next page and read about PWM in depth. Actually, is there... Hold on. PWM controller. There's a whole lot of like, yeah, I'm not entirely sure we're going to be doing any coding today. So here's what I am going to do. I'm going to expand this, going to bring it here, transition, so you guys can see a slightly bigger browser window. And we are just going to read. Right, give me a second. Let me hydrate, and then we're going to start reading this. Okay, so PWM in depth. Timer operation. The timer plays a key role in the PWM generator. It counts from 0 to a specified maximum value stored in a register, then resets and starts the cycle over. It counts from 0 to a specified maximum value. Okay, all right. This counting process determines the duration of one complete cycle called the period. Okay, all right, good to know. This, but um, if this counting process determines the duration of one complete cycle, how does that, no, how does that work then? Because I was assuming that the period was in seconds and you could specify the period yourself. So, like, how does that logic fit into this if you have to, if like, okay, the counting process determines the duration. How are you specifying the period if the counting process is determining the duration? I'm kind of confused about that. Okay, compare value. The timer's hardware, hold on. Okay, all right. The timer's hardware compares its current count with a compare value stored in a register. When the count is less than the compare value, the signal stays high. When the count exceeds the compare value, the signal goes low. Okay. All right. Okay. PWM resolution. I still haven't fully understood this, but let's continue reading. In PWM, resolution refers to how precisely the duty cycle can be controlled. This is determined by the number of bits used in the PWM's compare register. The counter, the timer counts from 0 to a maximum value based on the resolution. The higher the resolution, the more finely the duty cycle can be adjusted. All right, okay. For a system with n bits of resolution, the timer can count from 0 to 2 to the power n. Okay, all right. Oh, 2 to the power n minus 1. Yeah, that makes sense because it's starting from 0, which gives 2 to the power n possible levels for the duty cycle. Okay, for example, 8-bit resolution means 256. Okay, yeah. Uh, for example, 8-bit resolution allows the timer to count from 0 to 255, providing 256 possible duty cycle levels. Um, 10-bit resolution allows the timer to count from 0 to 1023, providing 1024 possible duty cycle levels. All right. Higher resolution gives more precise control over the duty cycle, but also means the timer must count more values within the same period, which could lower the frequency or require more processing power. That makes sense? Yep, that makes sense. Essentially, the resolution defines how many distinct duty cycle values can be set, with more bits offering finer adjustments. Okay. Simulation. You can modify the PWM resolution bits and duty cycle in this simulation. Adjusting the PWM resolution bits increases the maximum count, but remains within the time period. Adjusting the PWM resolution bits increases the maximum count. Okay, but remains within the time period. It does not affect the duty cycle. Okay. Um, Changing the duty cycle adjusts. Changing the duty cycle adjusts the on and off states accordingly, but it also stays within the period. Okay, I haven't fully understood what I just read, but let's try playing around with this. So we are looking at PWM. Okay. All right, so if we keep this to 4 bits, then we get 16 possible values, which makes sense because in 4 bits you can only fit a total of 16 values. Um, and then in 8 bits you can only fit a total of 256 values. So it does show here. I like that it's doing the drawing accordingly, and it's showing it in like steps. Okay, also the duty cycle. So when we adjust the duty cycle, so what this says is that let's say we set a 25% duty cycle. It's going to be high for that percentage of time, and then it's going to go low. It's going to be high. Okay, the time count. I I think the time count here is limited. Though no, the time count. Oh yeah, yeah. Okay, it mentions it here. Max timer count. So because I was going to be like, okay, the timer count, is it is it like limited to within 1 second, or what's the situation? But no, I think it's limited to um what would it be limited to? It's limited to 1 cycle. Oh, what did I just hit? Oh, I accidentally, yeah, close that. Yeah. Okay. Hold on just a second here. Are we dropping frames? No, I think we're good. Okay. Um, all right. Okay, so one duty cycle is how long one oscillation is. This is one duty cycle, right? And the entirety of this, what do you even call this entire thing? Is this entire thing the period? Um, this counting process determines the duration of one complete cycle called the period. Oh, so one entire cycle here is called the period. So what is this entire thing called? Because one duty cycle is this. So, um, 25% high and then 75% low. That's one entire duty cycle, right? And then you're going to have a number of such duty cycles depending on, well, you're going to have a number of such duty cycles within 1 second, depending on, um, I was about to say determined by, but yeah, depending on the frequency. So if you set a frequency of 5, you're going to have 5 duty cycles per second. So then one duty cycle is one period. Is that right? I'm not sure. Hold on, dude. For some reason, I'm yawning like crazy. Give me a second here. I don't know. Maybe I need to drink some more of my energy drink or what. Okay, let's try this again. Okay, so timer operation. Timer operation. The timer plays a key role In the PWM generator, it counts from 0 to a specified maximum value, um, then resets and starts the cycle over. This counting process determines the duration of one complete cycle called the period. Okay, all right. So what I'm if I'm understanding this correctly, this is the counting process. So it starts at 0 and it counts depending on what the resolution is. Um, it counts from 0 to a specified maximum value stored in a register. Yeah, because the value keeps repeating, so I'm guessing the maximum value is determined by the resolution. So if we are saying 8 bits, if it's an 8-bit resolution, then it's 256 values. So if it starts at 0, it counts to 255. All right. And then it resets and starts the cycle over, which is what we are seeing here. So it does this. Okay. All right. So this is showing us the timer, essentially. This is the timer. Um, for some reason, I was trying to connect this with what's happening here in the lower graph, but really this is just showing us the timer. And the timer determines, based on the timer, there's probably another system that determines what what the signal is going to be at that specific point in time within the duty cycle, depending on whatever percentage we have set. And yeah, that kind of makes sense, right? Because then what are we saying? So um, if it's 256, let's just take a half of that and say, I don't know, 127, which is like close. Yeah, let's say 127. And if we take a half of that, let's say 64, which is also close, kind of. That's 128 then. Close, yeah. So let's say 63. Um, so 25% would be around 63, 64, and whenever it does get to that point, which is somewhere here, if we have set the duty cycle to be 25%, once it gets here, then we crank this up to 8. So once we get to 60, 63, 64, then it drops. Okay, so this is showing us the counter, the timer. This is showing us the timer for each duty cycle, and then this is showing us what the signal is during that duty cycle. Okay, good. This is great because I've never actually had a chance to study this. I've never had a chance to look at it in this way. Um, so I'm excited to keep learning this. Um, sorry, zoned out. All right, compare value. The timer's hardware compares its current count with a compare value stored in a register. So I'm guessing the compare value is determined by the duty cycle. And so our compare value in the example I was just using, our compare value would probably be 63, 64. So when the count goes less than, no, wait, okay, I was wrong. When the count goes less than the compare value, the signal, oh, when the count is, no, I wasn't wrong. I wasn't wrong. When the count is less than the compare value, the signal stays high. And when the count exceeds the compare value, then the signal goes low. Awesome. Now I'm able to make sense out of this. Now I'm able to make sense out of this. But then, okay, what would be the difference between a period and a duty cycle? because what I'm understanding here, like what it's saying here, um, this counting process determines the duration of one complete cycle called the period. Let me ask Gemini. Hey, I do ESP32, or I'm learning ESP32 with no STD Rust. I'm confused about the difference between duty cycle and period in PWM. It's totally normal to get the two mixed up when you're first diving into bare metal Rust. When you're working with the ESP HAL or embedded HAL, you're often dealing with raw timer counts, which makes the distinction even more important. Think of PWM as a light switch that you are flipping on and off very, very fast. The period, that is the how often, the period is the total time it takes for one cycle, for one complete on off cycle to finish. It determines the frequency of your signal. For one complete on off cycle, how is that one on off cycle determining the entire frequency of the signal? No, no, no. I don't get that. Wait, I'm confused about that. In no STD Rust, I really shouldn't have mentioned no STD Rust. But okay, in no STD Rust, you usually define this setting. You usually define this by setting a top value or a max duty in your PWM configuration. Okay, the duty cycle is how long. Okay, what was the top one? How often? So the period is the frequency. Okay, the duty cycle is a percentage of the duty cycle is a percentage of that period that the signal oh, okay, the duty cycle is the percentage of that period that the signal remains on. So when we say our duty cycle is 25%, we mean that for 25% of the period, um, the signal is going to remain on. So the duty cycle is 25%. Okay, for why exactly was I relating the duty cycle to the entire period? So then like one entire on-off cycle is a period, and then the duty cycle is um it's telling us what percentage of that period is going to be on. Is the signal going to be on? Sorry, I hit my mic stand. For what percentage of that period is the signal going to be high or on? Okay, all right. Okay, so that helps put things into perspective. For some reason, I was considering um, duty cycle to mean the entire um, on off cycle. Dude, I don't know between yesterday and today how many times I've accidentally used the wrong terminology. Yeah, I'm not sure. Um, okay, rather than duty cycle to mean only to mean uh, the percentage of time or the percentage of, give me a second. To mean the percentage of the period that the signal um, stays on. I am confused about something though. You mentioned that the period determines the frequency, but if the period only represents one on-off cycle, how exactly is it determining the frequency? Isn't frequency, hold on, isn't frequency basically the number of on-off cycles or periods in a second? Spot on. You've actually answered your own question perfectly. The confusion usually comes from how we look at time versus how we look at rate. Okay. You are exactly right. Frequency is the number of cycles per second. The period is the duration of a single cycle. Because these are two sides of the same coin, if you change the length of one cycle, you inherently change. Oh, changing the length of the cycle. Okay. Okay, that makes sense. That makes sense. So if you make the length of a cycle zero 0.2, then your frequency is 5, isn't it? Yeah, yeah. If you make, yeah, okay. You inherently change how many of them can fit into 1 second. The mathematical link. In physics and electronics, they are inversely proportional. This is expressed by the formula F equals 1 divided by T. Frequency, which is hertz or cycles per second, and T is the period. A real world comparison, think of a metronome. The period is the time it takes for the arm to swing left, then right, and return to center. Let's say it takes zero 0.5 seconds. The frequency, if each cycle takes zero 0.5 seconds, you will hear 2 beats per second, so 2 hertz. If you make the period longer, say 2 seconds, the frequency drops to only zero 0.5 beats per second. Why this matters for your ESP32? Wait, no, hold on. So, what did Gemini say previously? The period is the total time it takes. Okay, so the I think I misunderstood what Gemini said. Gemini said word for word this. The period is the total time it takes for one complete on-off cycle to finish. It determines the frequency of your signal. That it is probably what confused me because I thought it is referring to the concept of a period and I should have been focusing on total time. So, like it, as in the total time that it takes for one complete on off cycle to finish, is what determines the frequency of your signal. So, if the total time that it takes for one on off cycle to finish is 0.2 seconds or 0.2 second, 0.2 second, then the frequency, which is cycles per second, would be zero 0.2 multiplied by, actually, um, I mean, I know this, but like I need to try and apply the math here. But like the frequency is 5. Frequency is 5, but like I'm trying to get it from the formula. So the formula is F equals 1 divided by T, meaning 1 divided by 0 0.2, and then that should give you 5. So your frequency is 5. I do have the Python thing here, so let's try that. Yeah, there we go. 5.0. You know what's interesting? With division, I've always had this issue of like what is divided by what. Um, and like I've had to, over time, I've had to try and come up with various visualizations that make it make sense in my head. So I can then assume that, oh yeah, this is supposed to go here, that is supposed to go there. Um, but yeah, yeah. All right. Okay, we can move on now. So relationship between duty cycle frequent. Oh God, is this about to explain what I just spent a bunch of time trying to understand? That's going to be so funny. Okay, hold on. The relationship between duty cycle, frequency, and resolution. This diagram illustrates, I mean, yeah, that makes sense, right? Duty cycle, frequency, and resolution. So the relationship would essentially be that um, one entire on-off cycle is a period. The duty cycle is a percentage of that period that the signal stays on. The frequency is basically how many of those periods fit within 1 second. And the resolution is basically how we are counting, or how many steps we are providing to count when we have, or how many steps we are providing to aid in the comparison operation to determine when we have reached the duty cycle percentage. And once we have reached that percentage, then we need to be able to take the signal low. So the resolution is what is what controls the number of steps. And so the resolution determines how accurate we can be timing wise. I hope I'm right about that. Let's see. This diagram illustrates the relationship between duty cycle, frequency, period, pulse width, and resolution. What is pulse width? Yeah, that should be, hold on. Yeah, I haven't looked into that. What would be considered pulse width here? Pulse width is the duration of, pulse width is basically duty cycle. So the pulse width is 50%. But like, is pulse width measured in like a different sort of, oh, the pulse width, it might be the count. I think that might be it. Yeah, yeah, the pulse width might be expressed because like duty cycle is measured in percentage, and that's fine. But the pulse width might be dependent on the resolution. So with the resolution, if I'm right about this, if pulse width um is basically this counter value, um then the pulse width with a resolution of 256 would be 127, or let's say 128. But the pulse width with a resolution of 1024 would be 512, if I'm getting that right. If I'm getting that right. This is really interesting, dude. Okay, okay. While it may seem a bit complex at first glance, breaking it down helps to clarify these concepts. Okay, in this example, the timer resolution is 4 bits, meaning the counter counts from 0 to 15. That makes sense. When the timer reaches its maximum value, an overflow interrupt is triggered, indicated by the blue arrow. Okay, and the counter is reset to 0. The time it takes for the timer to count from 0 to its maximum value is called as period. All right, okay, that's our period. The duty cycle is configured to 50%, meaning the signal remains high for half the period. At each step, at each step uh, in the counting process, the timer compares its current count with the duty cycle's compare value. So the duty cycle's compare value is 50%. I'm assuming if we are putting that in terms of value, then the counter is comparing that to 50% of um, what's the resolution? 4 bits. 50% of 16, so that's 8. When the timer count exceeds this compare value marked by the yellow arrow, the signal transitions from high to low. This triggers the compare interrupt, signaling the state change. The time during which the signal is high is referred to as the pulse width. The time during which the How is this measured though? Is this meant to be measured in seconds or okay, wait, no, I need to ask this question to Gemini. So I still have that conversation open. Okay, now wait, okay, this clears it up. Now I have a follow-up. Um, what is pulse width? How is it, no, what is it measured in? I should say what unit? What unit is it measured in? Also, if the PWM resolution, what do we call this? Like so far we're just saying resolution, right? Um, okay, I guess we're just calling it resolution. If the resolution is um, if the resolution controls how many if the resolution controls how many um, values the counter can count, what exactly are these values being counted called? Ticks? Okay, exactly. You've hit on the actual physical concept of what the hardware is doing. What is pulse width? Pulse width is the absolute amount of time the signal is high during a single period, while duty cycle is the percentage, a relative value. Pulse width is the duration, an absolute value. Okay, the relationship, pulse width is period multiplied by duty cycle. Yeah, that makes sense because then you're taking the duty cycle is essentially a percentage of the period, right? So then when you or the duty cycle is specifying what percentage of the period that the signal is going to stay high. And so what that formula gives you is called the pulse width. And the units, it is it is measured in units of time. Okay, typically milliseconds or microseconds. Why it matters? For some components like servos, the duty cycle percentage doesn't matter as much as the specific pulse width. A servo usually needs a pulse width of exactly 1.5 milliseconds to stay at center. I didn't know that. Okay. Regardless of whether your frequency is 50 hertz or 100 hertz. Then, what are the values being counted? You called it in the embedded world. These we call these ticks. A tick is the smallest unit of time the timer can quote unquote see. It represents one single oscillation of the clock source feeding the PWM peripheral. How resolution and ticks work together. The resolution in bits defines the maximum number of ticks the counter can reach before it has to reset. Okay, you know what? That's good enough for me. So we can now move on to the next thing, which is LED PWM controller. The ESP32 has LED PWM controller that generates PWM signals for controlling LEDs, example dimming effect. However, its functionality is limited to LEDs, isn't limited to LEDs. You can use it for other applications as well. If you're not familiar with PWM, I recommend you check the intro to PWM here. Okay. The LED-C includes 16 independent PWM generators and supports a maximum PWM duty cycle resolution of 20 bits. The 16 PWM channels further classified into what? Oh, are okay, yeah. The 16 PWM channels are further classified into two types: 8 high speed and 8 low speed channels. High speed versus low speed channels. High speed channels use hardware to automatically adjust the PWM duty cycle in a glitch free manner, ensuring smooth operation. In contrast, low speed channels rely on software to manually adjust the duty cycle. The PWM controller can automatically increase or decrease the duty cycle gradually, allowing for smooth fades without using the processor. Okay, the clock source. A clock source is a clock source in a microcontroller is like the heartbeat of the system. You know what? Real quick, we are talking about this clock, right? So far, we have encountered the concept of a clock, like, in terms of practically doing something with it. We have encountered the concept of a clock in PWM. I know for sure clocks come up in some of the protocols later on, in some of the like communication related stuff. So I want to see if this applies there as well, or if it's like a different, if they're different clocks. And even if they are different clocks, then does the clock, um, does the concept of a clock and the concept of um, duty cycle and stuff still apply there as well? Whatever we are learning here, will I be able to apply that there to understand? Because even there, you're using on-off signals um, in order to convey information. Though I believe in that case, your I believe in that case, each cycle is supposed to be either on or off. You're not doing like a half on, half off kind of thing. So it can be either on or off. And then based on whatever frequency has been set, whatever speed they've agreed on to read at, then they'll determine how to read whether how to read information basically, because when all they're receiving is on-off signals, they need to know where a byte starts and stops, or where whatever information they're looking for starts and stops. But yeah, hopefully what we are learning here, to a certain extent, it should apply there. I'm hoping. Okay, a clock source in a microcontroller is like the heartbeat of the system. It gives the microcontroller a regular quote unquote tick, which helps it keep track of time and coordinate all its tasks. In the ESP32, you can use different clock sources to manage the timers. Okay, so four high speed timers, four low speed timers, and it seems like you can use these four timers can be like split across 8 different channels, which is kind of interesting. Okay, there are four high-speed clock modules available, which can be assigned to high-speed channels. The high-speed timer module in the ESP32 can be clocked by sources such as so and so and so and so. In the ESP-HAL Rust library, these timers are represented by the timer number enum, which includes timer 0, 1, 2, and 3. Okay. There are also four low-speed clock modules available, which can be assigned to the low speed channels. These low speed timers can be clocked from either so and so so and so source. What can be clocked from either so and so or so and so. The slow clock source can be either the APB clock, which is 80 megahertz, or the 8 megahertz internal oscillator. Um, with the selection between these sources managed by so and so. The ESP-HAL also defines two enums, one for high-speed clock source and another for low-speed clock source. Currently, both enums have a single entry, so and so. All right. Um, for more details, refer to so and so and so and so. Yeah, I think I'm going to do that, because now we are actually looking into this controller. I have looked into this concept. Oh, that's not what I meant to do. I didn't think it was going to open up. I didn't think it was going to open up the. Either way, it's from Espressif. I thought it was going to open up the C++ like reference, but this opened up the PDF, which is fine. I didn't even know that there was this PDF, so that's good to know. Yeah, this actually gives more information than just the coding part of things, the coding side of things. Yeah, dude. Okay. Let's close this and continue here. Calculating PWM duty resolution. In the ESP-HAL, we need to specify both the duty resolution. That's what it's called, duty resolution. Okay. I was wondering, like, what do we prefix to resolution? I was just calling it PWM resolution, which is more or less the same thing, I guess. I'm not sure. And the frequency when configuring the timer object. Therefore, it's important to understand how to calculate the duty resolution from a desired frequency, and how to determine the frequency based on a given duty resolution. Um, these are the formulas taken from the ESP32's technical reference manual, but the variable names are simplified. Formula for PWM signal frequency. Oh, this is including, okay, this is including a bunch of stuff here. There's PWM signal frequency, there's PWM duty resolution formula. Signal frequency, signal frequency would be um 1 divided by the, no. Yeah, 1 divided by the period, right? 1 divided by the period would be the signal frequency. So if the period is 0.2, 1 divided by 2 is 5, meaning that period can repeat for, can take place a total of 5 times within that 1 second. So we have a frequency of 5. That's what the signal frequency would be, right? It says this divided by clock divider multiplied by 2 to the power of resolution bits. So clock divider multiplied by, let's say, 2 to the power of so and so, if we solve that first, because exponents should be solved first, right? PEMDAS? Yeah, yeah. So we solve the exponent first. Shit, I'm glad that I know PEMDAS, dude. That's holy shit. Okay, so let's say 256, no, not 256. Let's say, um, let's say 8 bits. Okay, so 256. What is clock divider going to be? Clock divider is the division factor for the clock source. What is clock supposed to be? Clock is the frequency of the clock source for the PWM timer. See, I'm confused here. Yeah. Resolution in bits is the duty resolution in bits. That's fine. Um, yeah, no, I'm confused about this. And then there's a duty resolution formula, which we are calculating in this way. Yeah, this is a little more complicated than what I was assuming it was going to be. Yeah, it's a tiny bit more complicated than what I was assuming it's going to be. I need to look into why any of this is necessary. Yeah, I need to understand why any of this is necessary. Do I need to calculate any of this? Or because there's a table here. So it says for 1 kilohertz, 5 kilohertz, 10 kilohertz, 1, 2, 1. Sorry, zoned out. Uh, I need to come back and read this later on, because I need to understand like what's going on here. I feel like I'm not fully grasping whatever is going on here. So we are calculating the duty resolution. Duty resolution gets used here because it mentions duty resolution in bits. I think the log 2 is, oh, this is logarithm. The log 2, or the logarithm, the base 2 logarithm. This is the base 2 logarithm of whatever this is. And base 2 logarithm would pretty much be, 2 raised to the power of what would give you so and so value. And here I'm glad that I know what logarithm is. Okay, this formula gives you, wait, this is the formula derived from the previous formula to calculate the desired duty resolution. Okay, this formula gives the duty resolution in bits, which represents the number of discrete levels available for the duty cycle of the PWM signal. That makes sense? Okay. Um, Calculating the highest resolution. The highest resolution is achieved with the clock divisor when the clock divisor is set to 1, meaning no division is applied to the clock. It's calculated as so and so. So that's the clock divided by the frequency multiplied by 1 for some reason. Am I getting that right? Am I getting that right? Is that dot supposed to be multiplication? I think so. Hold on, let's what is this? 80 million divided by 1000 multiplied by 1, which is just that. That gives us 80,000. Yeah, and then the log of 80,000, actually, I don't know, import math. Um, I don't know, dir math. Do we have log? We have log 2. We have log 2. Log 2 of 80,000. Log 2 is not defined. Math dot log 2 is 16. Okay, all right. Um, all right, okay. So the clock, what is LEDC clock supposed to be here? What is the value if that's supposed to be? Because for some reason that's coming up to 80 million. So I need to find out what LEDC clock is. This is a frequency of the clock source for the PWM timer. Oh, so this thing has a fixed resolution. Sorry, a fixed frequency. I think I need to look at that reference manual again, or I need to actually look at the reference manual. Okay, timer. It might be mentioning somewhere here. The clock of each high-speed timer, so and so, has two clocks. Ref this and that. For more information on the clock sources, read so and so. The input clock is divided down by divider first. The division factor is specified in so and so, which contains a fixed point number. Okay, let's take a look at reset and clock. Okay, reset, system clock. Um, all right. I'm trying to look for words that I know. I think APB clock is what we were looking at. Hold on. Clock source. For high power clocks, so and so, so and so. Okay. The ESP32 can use an external crystal oscillator, an internal PLL, or an oscillating circuit as as a clock source. Specifically, the clock sources available are high speed, and I'm trying to see how they got to. Oh, is it this? Okay, RC fast clock is an internal clock with a default frequency of 8 megahertz. Mega goes into the millions, doesn't it? Because you have kilo and no, that's wait, am I getting that right? So one, sorry, one, um, zero, no, one. So that's 100, and then this becomes uh, 1 kilohertz. So we have 1 hertz, 10 hertz, um, 100 hertz, 1 kilohertz, right? 10 kilohertz, 100 kilohertz, 1 megahertz. That's a million. Okay. Oh, I just realized you guys can't see this because I have the browser so big. Holy shit, I forgot about that. You guys can't see that. Well, you can kind of see the top thing, which shows the the Python window. Just so happens that it happens to be at the top, so you guys are able to see that to a certain extent, kind of, somewhat. Um, right. It says this frequency is adjustable. Okay, how? Okay, we going back here. Oh, it mentions information here. 80 megahertz, APB clock 80 megahertz, or the 8 megahertz internal oscillator. So the slow clock source can be either so and so or so and so. 80 is how we get 80 million here. Where is it? Here. 80 is how we get 80 million here. Thus, the highest resolution for a 1 kilohertz PWM signal using an 80 megahertz clock is 16 bits. All right. Yes, I am going to need to understand this because it seems like, okay, on one hand, you have the PWM frequency, right? But the thing that's actually doing the counting, the whole timer functionality, the clock that's responsible for that has its own frequency. And depending on what that frequency is, it's going to affect your calculations, which is why you need to calculate this. You need to calculate this stuff. So that's the highest. And then what's the lowest going to be? The division factor ranges from 1 to 1023 as per the data sheet. The lowest resolution is calculated when the clock divisor is at its maximum value. In this case, the clock divisor is 1023 plus 255 divided by 256. I don't get this at all. Like, why? Okay, this calculation gives the minimum number of bits required for a duty cycle control um, at the oh, um, wait, no, yeah, the minimum number of bits. Yeah, I'm confused about how this is fitting in with that. I need to sit and think about this for some time. Okay, all right. This calculation gives the minimum number of bits required for the duty cycle control at the specified PWM signal frequency. Sorry, zoned out. Thus, the lowest resolution for a 1 kilohertz PWM signal using an 80 megahertz clock is 7 bits. All right. Commonly used PWM frequencies and resolutions. This table is from the datasheet. This table is from the datasheet, summarizes the highest and lowest resolutions for common PWM frequencies with different clock sources. I need to come back to this and understand what I just read here because I haven't fully understood this. But we can move on from this for now. All right, then we have motor control pulse width modulator, MCPWM. All right, the ESP32 has two PWM peripherals, LED controller, and MCPWM. In this chapter, we will introduce the MCPWM. Okay, all right. I have a doubt that because I haven't fully understood the calculations in the previous one, I'm gonna have a little trouble understanding whatever is going on here as well. I'm not sure though. Let me see. Okay, motor control pulse width modulator. Oh wait, I already read that. MCPWM is designed for motor and power control. The ESP32 features two MCPWM units. Um, the diagram below provides an overview of a single MCPWM module. Okay, all right. Each MCPWM has prescaler, clock divider, three timers, three operators, fault handler, and a capture module. Sorry, zoned out. Okay. The prescaler is used to reduce the base clock frequency before it's applied to the PWM signal. The MCPWM is driven by a clock with a frequency of 160 megahertz, meaning it ticks 160 million times per second. This clock serves as the base frequency for the MCPWM module. Um, However, the prescaler modifies this base frequency by dividing it, effectively reducing the clock frequency that the PWM signal uses. To calculate the duration of each clock cycle, we take the inverse of the frequency, which gives us a period equals so and so, so and so. Okay, this means each clock cycle lasts 6.25 nanoseconds. Sorry, zoned out. Okay. Um, the PWM clock prescale register, 8 bits in the ESP32, allows you to adjust the base clock by dividing it. Once the prescaler is applied to the base clock, it effectively reduces the clock frequency. The resulting PWM period is calculated using the following formula. Yeah, dude, I am not getting this. I am not understanding this at all. Um, I don't know if I just need to come back to this. I think I need to come back to this later. Okay, the timer is responsible for counting up to a specified value, referred to as a period, at which point it resets and starts counting again. This helps control the frequency. This helps control the timing or frequency of the signal. Each timer has an 8-bit clock prescaler. It has 16-bit counter that can operate in 3 modes. In ESP-HAL, these are represented as enum, PWM working mode increase. This is counting up, where the timer starts at 0 and counts upwards to the period value before resetting, and then decrease, counting down, where the timer starts at the period value and counts down to 0 before resetting, counting up down. Oh, is it like a ping pong thing where the timer alternates between counting up and counting down, creating a symmetrical cycle? Okay. In ESP-HAL, the ESP-HAL has a timer clock config struct. Okay, all right. Operator. Dude, I'm gonna have to revisit both of these pages again because I'm gonna be honest, I haven't fully understood. Like, I understood up to PWM, but it seems like to implement PWM or to achieve PWM or to do PWM, um, the actual hardware that's required, that also has certain specifications, namely clock speed related specifications, which requires, due to which we need to um, do some calculations to figure out the precise timings. Um, yeah, I feel like that that part I haven't understood. Fortunately, I have understood the concept of PWM. So I've understood the higher level stuff. We just need to go down to the lower level stuff and understand how this is actually being implemented on the hardware level. So far, we've kind of understood the conceptual level, but how this is actually being implemented and achieved, that depends on the physical hardware's attributes. Okay, the PWM operator generates the desired output waveform using the timing references from the PWM timer. Each PWM operator features 2 outputs, PWM-A and PWM-B, with configurable dead time for both rising and falling edges. Okay, we have configured the MCPWM 0 peripheral and selected operator 0 to use the PWMXA output. Okay, okay. Yeah, you know what? I'm gonna have to revisit this whole thing. Let's read the summary of this. LED-C, or LED controller, is designed for controlling LEDs, but can also be used for doing general PWM tasks, making it ideal for basic applications like LED dimming and simple motor control. MCPWM, motor control PWM, is specifically built for motor control with advanced features like dead time insertion and fault handling, making it, give me a second. Okay. Um, Making it better suited for precise and complex motor control. Typical use cases of MCPWM peripherals as per the API reference document: digital motor control, example, brushed slash brushless DC motor, RC servo motor, switch mode based digital power conversion, power DAC, where duty cycle is equivalent to a DAC analog value, calculate external pulse width and convert it into other, wait, calculate external pulse width and convert it into other analog values like speed, distance, and then generate space vector PWM. Space vector PWM signals for field oriented control. I have never heard of this. Okay, for controlling a hobby servo motor like the SG90, that's what I have. These are those very small servo motors. LEDC is simple and sufficient, but MCPWM can also be used. All right. Okay. Now we are moving on to exciting things. So, LED fading effect. In this section, we will learn how to create a fading effect. I feel like I should understand the full calculation before I try to get into this. At least for LEDC, I should try to understand the full calculation before I get into this. Um, because I feel like I might be confused later on as to why certain values are being used. Though it is also very much possible that maybe the API kind of abstracts all that away. Maybe the library abstracts some of the lower level details away, and I don't need to worry too much about it. I will need to worry about it once we go into MCPWM or once we go into motor control stuff, specifically for robotics, because their timing is very precise timing is very important. But I wonder if there's something that can abstract away that detail. Okay, in this section, we will learn how to create a fading effect, i.e. reducing and increasing the brightness for an LED using the ESP32. First, we will fade the onboard LED, which is connected to GPIO2. I didn't know that that's possible. I thought I thought that we were limited to just digital on off. So digital zero and hold on. This is not DAC. This is not DAC. No. So something I didn't take into account is like, okay, we have GPIO pins that can only put out digital signals, right? PWM is not analog. PWM is digital, and it's creating the illusion of analog. So does that mean that every single GPIO pin can be used for PWM? No, no, there has to be something there. There has to be no, there has to be some bit of detail that I'm missing there. And I think I'll only understand this if I understand what's going on the lower level. Um, Only then will I understand, how this is being implemented. I feel like I should take the time to read this entire thing. Yeah, I feel like taking the time to read this entire thing. Maybe, not completely start to finish because holy shit, this is a lot of information. But like stuff specific to what I'm currently learning, I feel like I should take the time to read the specific sections for those things. Like currently, I'm learning PWM, right? Um, I don't know if there's a section specifically for PWM. I think there is. We had come to that section. By the way, real quick, I don't think I've ever seen this type of a PDF viewer. So that's kind of interesting to me. Um, yeah. There's also the fact that like the PDF that you're looking at, it should also be structured in a way that the index can be displayed like this. I rarely ever see um, indexes. I was about to say indices, but like I don't know if that applies here. I rarely ever see an index that's structured so well like this. Okay, so I see DMA there, memory organization, system and memory, eFuse. Okay, is there is there a way I can like search PWM? But what's it gonna search in? Oh God, it found so many. Um, oh, usually what I see is this, the pages version. Hold on, this is gonna freeze for a little bit. Yeah, usually what I see is this, but what I want to see is this, the document outline. Oh, okay. Uh, yeah, we are here. Hell yeah. Is this, what section is this? 28. So there's LED PWM and motor control PWM. Are these the only two types of PWMs that we have? Like, or is there like a general purpose PWM as well? I don't think I paid attention to that in the documentation. What did it mention there? Hold on. PWM in depth. Um, it has so and so. Yeah, it says that we have these, or maybe I'm looking at it the wrong way. Maybe what it's saying is that we have PWM functionality available. In general, PWM functionality is available. However, there are these two specific categories that you can use them in. One is the LED fading effect, and one is the MCPWM effect. Or wait, why did I say LED fading effect? LED controller. One is the LED controller, so the LED PWM or LEDC PWM, and the other is the MC PWM. You can use it in two different ways, and depending on how you're using it, it's going to use different hardware in different ways. I don't know. I don't know. I'm trying to wrap my head around this. Okay, okay. Um, right. Prerequisites to make the fading effect. We use a technique called PWM. Recommended to read so and so. Okay, we just got done with that. We will gradually increment the PWM's duty cycle to increase the brightness. Then we gradually decrement the PWM cycle to reduce the brightness of the LED. Okay, this effectively creates the fading effect on the LED. The eye. Come in closer, closer, because the more you think you see, the easier it'll be to fool you. Because what is seeing? You're looking, but what you're really doing is filtering, interpreting, searching for meaning. In PWM, we basically set a percentage to specify how long the signal stays high, and how long the signal stays high and low in each cycle. For instance, with a 50% duty cycle, the signal is on for half the time and off for the other half, making the LED light up for just half a cycle, for just half the cycle. Now, here's the cool part. When this switching happens super quickly, our eyes can't keep up. Instead, instead of seeing the blinking, it just looks like the brightness changes. The longer the LED stays on, the brighter it seems. The shorter it's on, the dimmer it looks. It's like tricking your brain into thinking the LED is smoothly dimming or brightening. PWM, the magician of electronics. All right, dude. You know what? We more or less started today's ESP32 study session with talking about how I was doing research through Gemini about how this whole dimming and brightening effect was really working, whether it was an illusion or not. And now we've sort of come full circle, I guess. Okay, writing Rust code for this. Okay, you know what? Um, Nah, you know what? We're not gonna do this today. We're gonna do this tomorrow because there's quite a bit to explore here. And before we explore any of this, I would really like to go back and understand those calculations that we read in both LEDC and in MCPWM. I would really like to understand how those calculations are working, why those calculations are necessary, um, though my guess is that those calculations are necessary specifically because the hardware that's implementing the clock, it has certain speeds and I think also certain limitations as to resolution. I don't remember if that's part of the issue. I think so. I think so. But yeah, there are certain very specific hardware limitations or specific I shouldn't say limitations, but very specific hardware attributes that impact the calculation. And I need to figure out exactly what is going on there. What are those attributes? What are the specifics that I should be knowing surrounding, PWM when it comes to low level hardware stuff? And hopefully I'm able to make sense out of these calculations that we were seeing earlier. Hold on. Here. Yeah. Hopefully I'm able to make sense out of these calculations and more specifically the need for these calculations. Once I'm comfortable with this, once I've understood these calculations, then the stuff over here is going to make a lot more sense to me. Because there are other things involved here, like they're mentioning clocks. Um, Hold on. There were certain variables being mentioned. So there's clock divider, there's something called RC fast clock, there's ref tick. All of this stuff I need to understand. And I guess the best way to understand it would be to read this side by side as well. I think so. I think so. Yeah, yeah. I think I'm gonna do that. All right. Um, Give me a second here. You know what? I don't think I'm gonna raid anyone today. Um, yeah, I'll just end here. Yeah, dude. I'll just end here and I'll stream again tomorrow, and tomorrow we'll make more progress. Hopefully, before tomorrow's stream, I will have already wrapped my head around this entire concept and well, the concept of this, these extra calculations and why they're necessary, how they work, and all of that stuff. Hopefully, I will have understood this before tomorrow's stream, and then we'll be able to do um, the LED fading effect practically. But yeah, dude, we made some good progress today. We made some decent progress today. I've gotten a much better understanding of PWM, way better than I had even yesterday. Um, I've got a pretty good understanding of PWM. PWM as a concept, as a high level concept. Now I need to understand how PWM is implemented on the low level. Um, and I'm going to do that off stream. That being said, I hope you guys have a nice day, and I'll see you all next time. Peace.